Okay. Okay. First of all, I would like to thanks for the invitation. This is a nice workshop, and I'm very happy to be here to introduce our recent work about the Dirac fermion in antiferromagnetic semimetal. And first of all, let me thanks for the collaborator. As Ben had mentioned, currently I am a postdoctor in Professor Shuchen Zhang's group, and in this work, the theoretical analysis part is mainly done by Quan Zhou, who is a PhD student in our group. And today and yesterday, there are many good introduction about the topological insulator, topological semimetal, wild semimetal, and Dirac nodal line, and I do not want to talk too much on that, and but I will give some brief introduction about this. And yesterday we have learned a lot about non-symmorphic group from the previous talk. So here I will give some brief introduction on this topic. Then I will present my calculation. So, as we all know, we could classify the solid states by electron filling, and for the semimetal, it's very interesting because we have a whole band has been filled. So around the Fermi level, we have zero density state, but if we have some small excitation, its transport behavior quite similar to the metal. And if we have a linear dispersion, if we have a linear dispersion on the semimetal on the Fermi level, so we could use some special equation to describe its low energy physics. While semimetal is more basic because it just needs two spin-polarized bands, and this kind of crossing can be described by a 2x2 matrix. And here we could define a Carroll anomaly by this. And for the three-dimensional wild semimetal, it's very robust. That means we cannot get it by using small perturbation. If we add some small perturbation, we just can shift the position of the wild point. If we want to gap the whole system, the only way is to mix two wild points with different clarity. And for the wild semimetal system, we do not have the double degeneracy for each band. That means we need break invariant symmetry or time reversal symmetry. If we break invariant symmetry, two wild points may linked by the time reversal symmetry, and time reversal symmetry will not change the sign of the clarity. That means in the whole system, at least we get 4 wild points. And if we break the time reversal symmetry, 2 wild points may linked by the invariant symmetry. Okay, so for this system, we may have 2 wild points. And on the side surface, we may have the Fermi arc. For the Fermi arc, I would like to say its Fermi surface state is a Riemann surface state. And this property, in fact, has been discussed when we discovered the wild fermion. And in this paper, which just published last week, they show the Riemann surface of the wild semimetal. That means if chemical potential cut electron parts and the whole parts, the Fermi arc behavior should be quite different. And in reality, we do observe this kind of Fermi arc on some real material, and Zhongkai will give a nice talk tomorrow about it, so I will do not talk too much on that. For the Dirac semimetal, we can consider is a copy of wild semimetal. That means at each double degenerate point, we have 2 wild points with opposite clarity. And just like I explained before, if we do not have additional symmetry to constrain, these 2 wild points will open a band gap. So that means for the Dirac semimetal, some additional symmetry is required. That could be rotation symmetry, that could be some crystal symmetry. And similar to wild semimetal, we also could observe the Fermi arc on the side surface. And it's a 2-dimensional surface state is also a Riemann surface state. Now for this finger, this part stands for spin up, this part stands for spin down. If we do not have the additional symmetry in this part, the smelt coupling will open band gap. So for the traditional Dirac semimetal, this is 2 candidates, its Fermi surface look like this. But if we have some additional symmetry, maybe non-symmetric symmetry, its Fermi surface like this. And this kind of crossing is protected by non-symmetric group. Okay, in fact, the Dirac semimetal has been experimentally discovered. One candidate is NA3B BI, and there are many people to talk about it. We do observe the Fermi arc on the side surface, and for the transport, some people claim they do observe the Carroll anomaly, charge pumping. And another candidate is this kind of material. Those 2 materials, the crossing point is protected by the rotation symmetry. And we have 2 Dirac points on the rotation axis. And for this kind of material, experiment also discovered it. And we have transport measurement to confirm this is a Dirac semimetal. But all of the discussed Dirac semimetal do not have magnetic property. So one question raised, can we observe Dirac semimetal in some antiferromagnetic system? For the ferromagnetic, every state is spin polarized, so we cannot get a double degenerate state. I mean, at cross point, it should be fourfold degenerate. And for the wild semimetal, in fact, the first wild semimetal is discovered in some antiferromagnetic system. So question is here, can we find Dirac semimetal in some antiferromagnetic system? It is possible, because the double degeneration is only guaranteed by the PT combination. P is invariant symmetry, T is time reversal symmetry. Invariant symmetry changes state K to minus K, and time reversal symmetry changes state K up to minus K down. So the combination guarantees a double degenerate at any K point. And if we only have one state, this kind of crossing should be guaranteed by some additional symmetry. But if we consider a double degenerate state, we need the degenerate state commute. Some symmetry guarantees that kind of crossing, and this symmetry should commute with the PT combination. And if the 2 states have different presentations, this kind of crossing, this kind of gapless crossing always exists there. And if these 2 states share different presentation with some crystal symmetry, a band gap will open. So this is the requirement for the Dirac semimetal in antiferromagnetic system. We need some special antiferromagnetic order, and we need found a special crystal symmetry. And the non-symmetric group gave us this opportunity. So non-symmetric group can be considered two parts. One is a symmetric group, the other is a half translation. And if we write down the eigenvalue of a non-symmetric group, it has two parts. One is eigenvalue for the symmetric group, the other is phase contribution by the half translation. Okay. And this is the argument from Charlie King's paper last year. He said if we have two states, okay, these two states have different lambda. Lambda is the symmetric group operation, the eigenvalue of the symmetric group operation. So that means at k equal, and this line is if we consider this operation is a rotation symmetry, and this line is the rotation axis, so at k equals 0 point, we have two states have different eigenvalue. And these two states, and here we also have the translation symmetry. That means the k equals g point, the total eigenvalue should be same. And here we have a phase contribution. That means for this state, they share same lambda. And for this state, they share same lambda. And the presentation of two states should be different. And here we always have a band crossing. This is the general argument. If we add the time reversal symmetry, do not consider the spin-out coupling. This is for the spinless system. At the time reversal invariant point, we always have a band crossing. And for the spinor system, we do consider time reversal symmetry. At the time reversal invariant point, we have a band crossing, and along this line. This is spin up state and spin down state. The spin up state and spin down state here, and here we also have the band crossing. And if we do have the invariant symmetry and the time reversal symmetry, the full band crossing will be at 1 point. So this kind of crossing is protected by non-symmetric group. And if we can found a non-symmetric group for some special material, it commutes with the PT combination. Okay, we can found that kind of band crossing, and this is our candidate material, and this material is copper, manganese, and arsenide. The magnetic moment is contributed by d orbital in the M atom. They have the antiferromagnetic ordering, and this kind of material has been experimentally discovered, and which is confirmed as a room temperature antiferromagnetic. And in this paper, they also do the calculations. They do observe the band crossing at some point, but they do not give a good explanation to that. And we repeat this calculation, the calculation for the formation energy. For the antiferromagnetic order, we confirm the ground state shares this kind of antiferromagnetic order. It do not break the combination between invariant symmetry and time reversal symmetry. Okay, this is symmetry argument for this kind of material. For this kind of material, we have antiferromagnetic order. So the time reversal symmetry is broken, invariant symmetry is broken, but the invariant symmetry and time reversal symmetry combination exist. Besides this symmetry, we also have a mirror symmetry and screw symmetry. Screw symmetry is non-symmetric symmetry, and we do some simple math for the relationship between the screw symmetry and PT combination. We found at kx equals pi and kz equals 0 should be xu line. Along this line, the screw symmetry commutes with the PT combination. That means if we have a band invariant for the screw symmetry, we can observe band crossing for along XU line. Okay, and this does not, this kind of crossing will not gapped by the spin-out coupling. Here is the electronic structure for this kind of material without spin-out coupling and without symmetry breaking. What we found? We found around Fermi level there exists a Dirac nodal line. The Dirac nodal line is a one-dimensional crossing in line in three-dimensional. Okay, and just like previous talk discussed, this kind of Dirac nodal line will contribute dome-like surface state. This is the green function calculation for the surface state. We do observe this kind of surface state, and for this kind of surface state, we also have the dispersion. So its cutoff looks like this, and this kind of surface state is protected by the mirror symmetry. Here, mirror symmetry is very subtle. It could be broken by the spin-out coupling. And I would emphasize for this kind of Dirac nodal line, if we have a loop which is like this, along this loop we could have a wild definition for the one-dimensional Z2 topological index. So this kind of drum-like surface state is protected by some topology. Okay, and if we try to break the mirror symmetry, the whole Dirac nodal line will gap at some point, but at 4 points, here, here, and here, we have 4 Dirac points. Okay, 2 of them is protected by the screw symmetry, and they share the same clarity charge. So the other, so in this system, the total number for the Dirac semimetals should be 4. And here we do not consider spin-out coupling. So for each spin, it should be a wild semimetal. Okay, and then we calculate the Fermi arc for each spin, because each spin is the wild semimetal. So we do observe the Fermi arc for each spin. And here I would like to emphasize one point is that here the clarity is linked with the spin. Okay, so for spin up state, it has one kind of clarity, and for spin down state, we have another. Okay, let's move on. When we consider spin-out coupling, and the magnetization is along 001 direction, the screw symmetry is not broken. So we have a gapless point here, and we do observe the Fermi arc. And this kind of Fermi arc is similar to the Fleur's discussion. The Fermi surface should be a Riemann surface. Okay, and besides the band crossing here, which is protected by the non-symmetric symmetry, the other point will be gapped by spin-out coupling. And okay, sorry. Okay, and if we apply a strong magnetic field along the direction, this kind of magnetic field will not break the screw symmetry. So, but the PT combination, we do not have the PT combination. So each state will split to spin polarized state, and for the coupled crossing point here, will split it two wild point here. This argument is similar to Charlie King's argument in his PL paper, and for this kind of material, in this situation, it should be it will have many wild points. And I also would like to say the electronic structure in this kind of material depends on the magnetic orientation, because if the magnetic orientation points to the other direction, the screw symmetry will be broken. So if a screw symmetry, we do not have screw symmetry, the gapless points we will lose the gapless point. Yes. And then we calculate MAE for this kind of material. We found the easy magnetic axis is along x direction. So that means in this kind of intrinsic material, we cannot observe the gapless points, but we could tune its magnetic property by using some ferromagnetic substrate. The ferromagnetic substrate will contribute a large exchange anisotropy, and based on our calculations, the ferromagnetic substrate will stabilize the magnetic orientation along z direction, and the MAE will be enhanced to 7.1 MeV per M atom, and this value is larger, almost one order of magnitude than the intrinsic one. Yes. And we also found this kind of crossing depends on onset potential, depends on interaction. If we add some interaction effect on the d orbital of M atom, a topological phase transition may occur here. And this is a phase diagram for this kind of material. In this part, we do have the topological non-trivial phase, and in this part, we lose it. And if the band invariant also exists there, we show the interesting physics always exists in this material. Okay, this is a summary for my talk. We found antiferromagnetic Dirac semimetal in a real material. We found some interesting physics here. We do observe the Dirac nodal line when we do not consider Semimeltals coupling and keep mirror symmetry. If we break mirror symmetry, do not consider Semimeltals coupling, we found a Dirac semimetal whose clarity is linked with its spin. And if we consider Semimeltals coupling and keep the non-symmorphic symmetry, we have a coupled wire fermion. And for the coupled wire fermion, we always have the interesting fermionic state. And if we break everything, here we just get a semimetal without degeneracy protected by some additional symmetry. Okay, that's all. Thank you.